Bismillahirrahmanirrahim. Assalamu alaikum, my dear student. I am Engineer Hassan Khan, your instructor for Engineering Hydrology subject, and today we will discuss lecture number 7 of this subject. In this lecture, we will cover analysis of precipitation data, which consists of estimation of missing precipitation data and consistency of precipitation data. The analysis of precipitation data actually consists of 3 parts. In the first part, if we collect the data in some station doesn't give or doesn't record any type of data during recording time, so what will we do for that data which is missing at some station, but at other station in the surrounding it is available? So we can estimate this missing precipitation data by a method we will discuss in this lecture. The second, if the data is collected from all the station and it is okay, then before using this data in the hydrological analysis of any structure, first we have to check the consistency of this precipitation data. Either this precipitation data is consistent or not. If it is consistent, then it is okay, and if it is not consistent, then we will make it consistent by using a double mass index or double mass curve method. The third one, which comes under the analysis of precipitation data, is the estimation of average precipitation over a basin. And this we will discuss in the upcoming lectures. So first topic is the estimation of missing precipitation data. As we have already discussed, some of the precipitation station may have breaks in the record because of absence of the observer or because of some other failure or error, such as instrumental failure. It is often necessary to estimate this missing record. Now, to estimate this record, we will use the US Weather Bureau method, in which the missing precipitation of a station is estimated from the observations of precipitation at some other stations as close to and as nearly as evenly spaced around the station with the missing record as possible. Now, there are 2 types of stations in this situation. One is the station whose data is missing. This station is known as interpolation station. And all other stations from the help of which we are estimating the data for the interpolation station are known as index stations. All other stations in the surrounding are known as index stations. So for the estimation of missing precipitation data, we have 2 methods. Number 1 is the simple arithmetic mean method, and number 2 is normal ratio method. So first let's discuss the simple arithmetic mean method. According to the simple arithmetic mean method, the missing precipitation of any station X is given as this: Px, missing precipitation at station X, is equal to 1 by n summation of Pi, where I starting from 1 to n. This is a formula written in the summation form, as you have already known this summation form. N in this formula, small n, is the number of nearby stations. Nearby stations mean the index stations. Pi is precipitation at the ith station. Ith mean station 1, station 2, station 3, station 4, and up to station n. Index stations. Okay, if we expand this formula for 3 stations with the name of 1, 2, and 3, then the formula becomes like this: P1 plus P2 plus P3 divided by 3. Remember, these three are all the index stations and the Px is the interpolation station. If we name the stations by ABC, then we can write this formula in expanded form like this. Okay. Now the second method is the normal ratio method. According to the normal ratio method, the missing precipitation of a station X is given by this formula. As the name represents in this method, the normal ratio is used. Normal ratio. Nx by Ni. This is known as the normal ratio. Nx is the normal annual precipitation of the X station, and Ni is the normal annual precipitation of the ith station. Pi is the storm precipitation of the ith station. Px is the storm precipitation of the interpolation station which is missing, and n is the number of index stations. Okay. If we expand this formula for 3 stations, for 3 index stations, then the formula becomes like this. Px is 1 divided by 3 bracket nx divided by n1 multiplied by p1 plus nx divided by n2 multiplied by p2 plus nx divided by n3 multiplied by p3. Now there are 2 methods for estimation of missing precipitation data. Now which one we will use? It depends upon the data. It depends upon especially the normal annual precipitation of the index stations. There is a condition which will determine that either we have to use the normal ratio method or the simple arithmetic mean method. Remember, the simplest method is the simple arithmetic mean method. But in some cases this is not applicable. This is only applicable if the rainfall is uniformly distributed over the whole area. And this uniform distribution you can find out by checking the normal annual precipitation of all the index stations. For this, the criteria is like this. If the normal annual precipitation of the index stations lies within plus minus 10% of normal annual precipitation of interpolation station, then we can use simple arithmetic mean method to determine the missing precipitation record. Otherwise, normal ratio method will be used. Consider that record is missing from station X. Now let N, capital N, is the normal annual precipitation. Normal annual precipitation is actually mean of 30 years of annual precipitation data. P is the storm precipitation. Now let Px be the missing precipitation for station X and Nx. Then the normal annual precipitation of this station Na, Nb and Nc are normal annual precipitation of nearby 3 stations A, B and C respectively, while Pa, Pb and Pc are the storm precipitation of station A, station B, station C. Now we have to compare Nx with Na, normal annual precipitation of the station X, with normal annual precipitation of station A, normal annual precipitation of station B and normal annual precipitation of station C separately. If difference of Nx minus Na, Nx minus Nb, Nx minus Nc is within 10% of Nx, then we can use simple arithmetic mean method. Otherwise, the normal ratio method will be used. For explanation and for further exploration of this criteria, we have a simple example. You can simply understand this plus minus 10% criteria. Now let's see this example. Example says that find out the missing storm precipitation of station C given in the following table. Here it is a table, and this row represents the station. Total stations are A, B, C, D, E, 5, and which at one station, at station C, a specific rainfall data is missing. Okay, and the same rainfall data at other station has been calculated at station A, B, C, A, B, D, and E. But at station C and all other stations, we have the normal annual precipitation, which is the average of almost 30 years of precipitation data. At all stations, we have the normal annual precipitation data available. So in this case, we have to calculate the missing precipitation, missing storm precipitation of station C. Okay. So first of all, we have to check that whether the simple arithmetic mean method will be used or normal ratio method will be applied. Okay. So for this purpose, let's find out 10% of NC. NC means normal annual precipitation of station C, which is 93.5. So 10% of this means 93.5 multiplied by 10 divided by 100, which is 9.35. Now add this 10% of NC with NC to get like 93.5 is the value of NC, normal annual precipitation at station C, plus 10% of NC is 9.35, which becomes 102.85. Similarly, subtract this 10% from the value of NC. NC is 93.5 minus 9.35, you will get 84.15. Now, it gives us a range from 84.15 to 102.85. This is a range. Now check all other n values, all other normal annual precipitation values. If they occurs within this range, if they are within this range, then you can use the simple arithmetic mean method. Otherwise, if any value, if any one of the normal annual precipitation value exceed this range, either one side or the other side, so then we have to use the normal ratio method. Okay, now it is clear from data in table above that NB is 109.5, ND is 125.7, and NE is 117.5. and NA is 100.3, NB is 109.5, ND is 125.7, and NE is 117.5. Now you have the range of 84.15 to 102.85. Now it is clear that NB value, ND value, and NE value, these all three values are out of this range. So in this case, in this example, we will use this normal ratio method. Okay. Now according to the normal ratio method, we will write the formula in this form. PC is the missing storm precipitation at station C, which is equal to 1 divided by n summation of n, 1 divided by n summation of NC into PI, NC divided by NI into PI, where I starting from 1 to n. And here are the index station are how much? Station A, station B, station D, and station E. So there are 4 stations. So putting the value of n is 4 and expanding this formula for the current situation, you will get 1 divided by 4 nc by na into pa plus nc by nb into pb plus nc by nd into pd plus nc by ne into pe, which implies that pc, now you can see in all these terms nc is common, so we can take nc out of the bracket. So pc is equal to 1 divided by 4 multiplied by nc multiplied by the bracket, which is pa divided by na plus pb divided by nb plus pd divided by nd plus pe divided by ne. This implies that pc is equal to 1 divided by 4 into 93.5 multiplied by putting all the values of nc, pa, pd, pd, pe and n. So we will get this after calculating this ratio. We will get this, and then finally multiplying 23.3 multiplied by, we will get the PC value as 7.8 centimeter, and this is the answer. Here it is a second example. In the second example, the data, I think this is very simple example, the same example, just difference in this in these both are the data. In this example, the data is given in explanation form, and in the first, the data was given in the tabular form. Here you can see precipitation station X was inoperative for part of a month during which a storm occurred. The storm totaled at 3 surrounding stations A, B, and C were respectively 10.7, 8.9, and 12.2 centimeter. The normal annual precipitation amounts at stations X, A, B, and C are respectively 97.8, 112, 93.5, and 119.9 centimeter. Estimate the storm precipitation for station X. The same example. First, we have to check either we will use the simple arithmetic mean method or the normal ratio method will be used. So for this purpose, we have to calculate 10% of the nx, which is 97.8. So here the 10% will be 9.78, and then 8 this 9.78 with the 97.8 to get a value, and then check that either all the value are within the range or out of the range. But in this example, we will do this by another method, by the difference method. Here precipitation at station A is 10.7 centimeter, at station B it is 8.90 centimeter, at station C it is 12.2 centimeter, and at station X it is unknown. The normal annual precipitation of all stations are given. So first of all, 10% of nx is how much? It is 9.78 centimeter. Now the second method will be like this: nx minus na. Nx, which is 97.8, minus na is which is 112, so it becomes minus 14.2 centimeter, which is more than 10% of plus minus 10% of nx, which is 9.78. So if this difference, if any one of them like nx minus nb or nx minus nc, any one of these is less than 10% of nx, which is 9.78 centimeter, then it's mean that no need of calculating nx minus nb and nx minus nc. So it means that we will use the the normal ratio method, and according to which you know the formula 1 divided by n multiplied by nx minus ni multiplied by pi. expanding this for these 3 index station and putting the values here in the formula, which is 1 divided by 3. This is, you can see nx multiplied by p, nx multiplied by pa divided by n divided by na. Similarly, nx multiplied by pb divided by nb, and so on. Calculating this, which is simple multiplication and division, and you can find out the missing storm precipitation to be 9.5 centimeter. Okay, the next is consistency of precipitation data or double mass analysis. In using precipitation in the solution of hydrologic problems, it is necessary to ascertain the time trends in the data are due to meteorological changes. You know, when we have to use this precipitation data in any hydrological problem, first we have to check this data that all the changes in the data are due to the time trends or the meteorological changes. But sometimes these trends are the results of the changes in the gauge location, changes in the intermediate surroundings such as construction of buildings or growth of trees, etc., and changes in the observation techniques. So due to such changes, the data might not be consistent. So the consistency of the record is required to be determined and the necessary adjustment be made. This can be achieved by the method called the double mass curve technique. Now we will learn the double mass curve technique, how to carry out the double mass curve technique, and then we will solve a simple example on the double mass curve technique. So inshallah you will understand it very clear. So the double mass curve is obtained by plotting the accumulated precipitation. Accumulated means the summation of all accumulated precipitation at the station in question along y-axis and the average accumulated precipitation of a number of other nearby stations which are situated under the same meteorological conditions along x-axis. Now if the curve has a constant slope, the record of station X is consistent. However, if there is any break in the slope of the curve, the record of the station is inconsistent and has to be adjusted by this formula. P adjusted will be equal to the ratio of the slope multiplied by the P observed, the observed precipitation. Okay. By this method, we mean that a graph, a plot will be drawn of the data. We will have two types of data: the precipitation of the station in the question, which we are determining consistency for, and the second is the average precipitation of the surrounding stations. Okay, so we will convert the precipitation of the station to accumulated precipitation and similarly find out the accumulated precipitation for the average of the surrounding stations. Okay, the accumulated average of the surrounding station will be plotted along the x-axis and the precipitation of the station in the question will be plotted along the y-axis, this curve. Now if the curve is just straight line like this, then it means that the data is consistent. But if this graph has some breaks, like its slopes is different, and up to this point the slope is different, and after this point the slope is like this, so it means that the data up to this point is okay, but beyond this point the data is inconsistent and it can be made consistent by using this formula. Okay, now in this formula the P adjusted, this is the consistent precipitation, adjusted precipitation. P naught is the given precipitation, which is observed precipitation, which have the inconsistency in this portion. SA is the slope of this line, and S naught is the slope of this line, mean the slope before the break and the slope after the break. Okay, now for this we have a example, and you can see this example. The question of the example is the check consistency of the data given in table below and adjust it if it is found to be inconsistent. Okay, now in this example we have three columns. Remember, in this table we have three columns. Number one is year, the second one is annual precipitation at station X in millimeter, and the third is mean of annual precipitation of 20 surrounding stations in millimeter. Again the repetition of the year, annual precipitation, and mean of annual precipitation. So if we look at the years start from 72, 71, 77, 70, 69, 68, 67. Similarly, the last one in this column is 1955. Okay, and after this 1954, 1953. So it means that this is in descending order. If the data is not in this descending order, first of all you have to make the data in the descending order. Why? Because you know the data which is the latest one, the 1972, is more reliable as compared to the data which is the farthest, the 1940 or 1937. So the data which is more reliable, you think it should be consistent, should be at the start. Like 1972 is at the start, 1971, 70, 69, and so on. So the annual precipitation at station X is here given, and similarly the mean of the surrounding station is also given. So what we will do, first we will convert this annual precipitation into a cumulative annual precipitation. Find out the accumulative of this, and then accumulative of this column. So we will add up two more columns of accumulative of annual precipitation at station X and accumulative of mean of annual precipitation of 20 surrounding stations. Okay, after that we will plot a graph. So let's do all this in Excel. So I have already done this all calculation in the Excel sheet, but I'll explain it for you. Okay, here you can see the year, the same example data, the year, annual precipitation at station X in millimeter, mean of annual precipitation of 20 surrounding stations. Now this data, these three columns are already given in the example. The data is starting from 1972 to 1937. Precipitation of station, mean of annual precipitation of 20 surrounding stations. So cumulative annual precipitation at station X. All these calculations you can simply solve in the Excel, as you can see here. This is how cumulative you can calculate. The cumulative for the first 1972 year is the same 188. For the second it would be like 188 plus 185, 185 plus 188, both of them. So the formula for this is G5, which is this one. G5, the G5 is 188 plus E6, which is 185. Okay, and then accumulative of the next will be what? This one multiplied by this one. So all these three. Similarly, adding this up to the end, so the cumulative of the last 1937 will be this much. Similarly, cumulative precipitation of the mean of annual precipitation. Cumulative of mean of annual precipitation 20 surrounding station. You can find it by this one. After this, we will select both of them, both the cumulative column, and insert and go to the insert and select the scatter diagram, the line one, and draw this curve. So after plotting the curve, you can see here the curve is like this. So the curve up to this point, the red point, as you can see, it is straight, and after the red point the slope of the curve changes. Before it is, the slope is this one, and after that is it. So first of all, you have to find out this point. So if you bring the cursor on this point, you can see the coordinates of this point is how much? 6770 is the x coordinate, is 1, and similarly the y coordinate is 5836. Now check this value in these two columns, the cumulative columns. You can see this value is here, this and this. So this is actually the break point. So before the break, the data is consistent, and after the break, the data is inconsistent. So first of all, find from this break point, we can find that up to the year 1950, the data is consistent, and before 1950, mean 1949, 1948 up to 1937, the data is inconsistent. So what we will do, first we have to calculate the slope for this portion, for the first portion, and then for the second portion. So for the first portion, the slope is like this. It is simple, just write down equal sign, then slope, and select the data, the x and the y data. This is the y range and this is the x range. The y range is up to 1950, it is to be clear, and similarly the x range up to 1950, and press enter. So you will get the slope of this first portion, which is 0.8667, or you can say 0.867. Similarly, for the second portion, for the last portion, you can find the slope for this one. The slope, the x value on the second portion and the y value. This is simple formula. So this slope for this portion is 1.169. Now the slope ratio, mean the SA divided by S0, is equal to how much? 0.74. The slope ratio is 0.74. This is actually what? Actually SA. Okay, and this is S0. S0. Okay. And what is this? This is the slope ratio. Slope ratio mean SA divided by S0. Okay, so we have find out the slope ratio. Now just the portion beyond 1950 of the precipitation, we have to multiply this portion. Remember, this data will be multiplied with how much? With this slope ratio, 0.74. So the data above mean up to 1950, from 1972 to 1950 is consistent and need no correction. So the data is the same as given. But the data after before 1950 mean 1949 is to be multiplied by this slope ratio 0.74. So this data is multiplied by this one. So the data, the value of all these values are multiplied with this. You can see in the formula, this is the value, this one multiplied by this. Okay, so we have find the corrected precipitation of 1949 was how much? 210.5. Instead of 284, it is how much? Annual precipitation. Annual precipitation of 1949 is how much? 210.5 millimeter. Similarly, 1948 is 493, which was not correct, and the correct is 365.4 millimeter. Okay, I think it's okay for this. So the same solution is given over here. This is the example. A double mass curve is plotted by taking cumulative of average precipitation of surrounding station along x-axis and cumulative precipitation of station x along y-axis, for which consistency of data is to be investigated. The figure is like this one. You know the formula. PA is A by S naught multiplied by P naught. Is A is the slope of this portion, S naught is the slope of this portion. Okay, so this slope and this slope has already been found out in the Excel sheet, and then the slope ratio is also calculated, and then the slope ratio is multiplied with this portion of the data. Okay, so the correction for slope is applied to readings beyond break in the slope. The calculation of slope of first line before the break is 0.867 from Excel sheet. You know, slope of deviating line after the break is 1.169. So correction to values multiplying factor is how much? Is A by S naught, which is 0.74. So up to 1950 no correction is required. Before 1950 all readings are multiplied by slope ratio of this to get the corrected value. Okay, so this is the data from 1972 to 1950 which needs no correction. The same precipitation data. Okay, and this is the data from 1949 to 1937, and the data is actually this one, and this is the corrected precipitation data. This comes after multiplication with 0.74. Okay, I think this is enough for today's lecture, and again my recommended textbooks in reading references are given. As you know, I am usually using this first one, K. Subramania Engineering Hydrology. Okay, thank you. Again, I'm Engineer Hassan Khan, and if you have any question, issue, or any problem, you can contact me through my email address hassan.seval@soot.edu.pk.